Okay, so this is the sixth free response questions problem. So this is one that has a table. In the stem, the first question says use a left Riemann sum with 3 subintervals to approximate the volume of the tank, indicate your units of measure. So if I do this, I want the volume to be the integral from 0 to 10 of A of H dH, which using left Riemann sums is going to be approximated by 50.3 with a width of 2 plus 14.4 with a width of 3 and 6.5 with a width of 5, which is 176.3 cubic feet. All right, so part B asks, is this an overestimation or an underestimation? The easiest way to kind of get your head around this is to actually draw the picture, because the first left hand is at 50.3. The second left hand is at 4.4. The third left hand is at 6.5. Right? And then it goes down to 2.9, but we never actually used that, right? So there's like your 2.9. And basically, if you look at the stem of the problem, they tell us that the A of H is decreasing. So if it's decreasing, whatever is going on here with the function, this is extraneous. So A of H decreasing is going to imply an overestimation. All right, so let's move on to parts C and D. Part C says that we actually now have an actual function to model the area of each of the cross sections. So once the volume, this is just volume is an accumulation of area type problem. So volume is going to be the integral from 0 to 10 of this f of h dh, which when you put that into the calculator, this is part C, you're getting 101.325 cubic feet. So that one's pretty straightforward. Part D asks, water is pumped into the tank. So this is like a related rates problem. When the height of the water is 5 feet, so when height is 5, dH dt is 0.26 feet per minute. We want to use the model above to find the rate at which the volume is changing with respect to time. All right, so volume here is the integral from 0 to height of f of h dh, right? Or f of x, you have to have two different variables there. F of x dx, which means that dv dt is going to be f of h times dh dt. Okay, but we want this when h is 5, right? So you have to do a little bit of, not a whole lot, right? I think we got it, right? H of 5, so we want f of 5 times 0.26, right? Which should give me 1.694 cubic feet per minute. All right, so there's that problem. You just throw the 5 into that f of x or f of h problem, and then you multiply it by the dHdt, and you get the related rate. All right, so let's move on to number 2. All right, so in problem number 2, they're giving us a graph to work from and some data. The graph goes from -6 to 5. The data here is that f of -2 is 7. The graph is the derivative, and we get line segments in a semicircle. So the first thing is what's the value of f of -6 and the f of value 5. All right, so you can use fundamental theory of calculus for both of these. So we can go from -6 to -2 of f prime of x dx. Should give me f of -2 minus f of -6. All right, so this is just a triangle. So this is like 1/2 of the base of 4 and a height of 2. F of -2 is clearly 7. So what's this? This is 4 is 7 minus f of -6, which means that f of -6 should be 3. Okay, so that's not so bad. Do the same idea with the 5. So take the integral from -2 to 5. F prime of x dx should be f of not correct. F of 5 minus f of -2. So this is a semicircle. The radius 2, so that's going to give me 4 pi divided by 2 is 2 pi, so that's -2 pi plus a triangle, which is 1/2 base times height. F of 5 is what we're trying to find, and we know that that's 7, so this is -2 pi plus 3 is f of 5 minus 7, which means f of 5 should be 10 minus 2 pi. All right, so that's part A. Let's move on to part B. Part B of the problem asks on what intervals is f increasing. So f is going to increase when f prime of x is positive. So this happens on the intervals from -6 to -2 and 2 to 5. A little weirdness about the BC exam is that when they're talking about increasing, decreasing, they actually want closed intervals. So we're going to say that it's that, and it's this. The scoring guides give you closed intervals on these. I don't know the rationale completely behind it, but they are consistent about that. So there's a little tidbit for your practice there. Let's look at part C, and what's the absolute minimum, right? So we look at where is the derivative 0 and the endpoints. So we get a set of critical points. With the endpoint -6, we have a derivative at 0 at -2. We have a derivative at 0 at 2. And we have an endpoint and a derivative at 0 at 5. So we have to test those. F of -6 we already found was 3. F of -2 we're given, that's 7. F of 2, well, if you think about that, that's going to be that quarter circle again. So or that half circle. So you're going to take the 7, and then you're going to subtract the half circle. Now, this is approximately 7 minus 6.28, which is about 0.72. And f of 5 we already found was 10 minus 2 pi. So that's our winner. That's our minimum. The minimum is 7 minus 2 pi. All right, so let's look at part D of the problem. All right, so part D here is which f double prime of -5 or f double prime of 3. Find the value of each, and if it doesn't exist, explain why. So if I have the derivative, that's the graph, then I can find the second derivative by looking at the slopes. So the slope at -5 can be used by like -2/4, which is just -1/2. So that one's pretty easy. The problem is that like f prime of 3 is a cusp there. So you have to make a statement. You have to say like that the limit as x approaches 3 from the left of f double prime of 3 is 2, and that the limit as x approaches 3 from the right of f double prime of 3 is equal to -1, and these things don't equal, so that tells me that the second derivative at 3 does not exist. Alright, so there's part D. Alright, so section 3 or page 3 of this is a lot of information about a cooling potato. You're given a differential equation there and an initial value. So the differential equation is the cooling rate, and the cooling at the temperature at time 0 is 91. So if you look at A, it wants a linear approximation, and then to use that linear approximation to find time 3. So you know h of 0 is 91. You know that the rate of change with respect to time when time is 0 is going to be, this is the tricky bit because you don't put a 0 here. You put a 91 there because that's an h, not a t. Okay, so this is minus 27. There we go. So this is going to be -1/4 times 64, which is -16, which means, okay, so it's h minus h at time 0 is equal to -16 t at 0, right? So this is h minus 91 is equal to -16 t, which is h is equal to -16 t plus 91. So that's your linear approximation. We want h time 3, which would be -16 times 3 plus 91, which gives me 43 degrees Celsius. So there you go. That's problem A. All right, so problem B asks, is this an over or an under approximation? It says use the second derivative to do that. So the first derivative with respect to time is -1/4 h minus 27. So the second derivative with respect to time, remember this is implicit because this is an h, not a t, is -1/4 times dh dt, which is -1/4 times, well, let's back this up. We don't have to like do a whole lot of work there because we want specifically what is this value at the point of approximation, which is when t is 0. So this is going to be -1/4, and we know that dh dt at time 0 is -16. We found that above. So that means this is going to give me 4, which is bigger than 0, which means I am concave up at this point. So I'm cooling, right? So here's my line, my linear approximation. This is time t equals 0. I'm cooling, so if I'm concave up and I have agreement at that point in the approximation and I'm concave up, this is the actual cooling curve. This is the linear approximation. This is time 3, which means that the estimate, which is this one, as opposed to the actual cooling, is an underestimate. And that's because I'm decreasing with a positive second derivative. All right. So let's look at part C. All right. So part C says, hey, guess what? We found a better way to try to figure this all out, and we're going to give you a different cooling curve. And we're going to make this one dg dt is equal to negative g minus 27 to the 2/3. Okay, so what this wants is it wants me to find a way to come up with g, given the initial value of at time 0 we're at temperature 91, and then use that for another approximation at time 3. So if you play out the separation of variables here, you're going to get negative g minus 27 to the negative 2/3 dg is equal to dt. And then we just integrate both sides. All right, so we're going to get g minus 27 here, and this is going to go to the 1/3. So I need a 3 there. The derivative of the inside is 1, so that helps me. T plus c. All right, so now we got to use the initial value to find c. Well, the temperature is 91 degrees at time 0. 3. There we go. So this is negative 3 times 64 to the third. This is a third. Equals c. So this is going to be negative 3 times 4, which is c, which means c is negative 12. All right, so that gives me the curve, right? So negative 3 g minus 27 to the 1/3 is t minus 12. All right, so divide by negative 3, get g minus 27 to the 1/3 is negative t over 3 plus 4. Cube everything. G minus 27 is there we go, is negative t over 3 plus 4 cubed, and then isolate the g. Negative t over 3 plus 4 cubed plus 27. All right, so there's your g function. I want g at time 3, so this is going to give me negative 1 plus 4 cubed plus 27. That's 3 cubed plus 27, which is 54 degrees Celsius using this different model. All right, so that's problem 3. Let's do number 4. All right, so looking at problem 4, they give me a function f. They ask me first to find the slope at 3. So that's just take the derivative of f. You can use the quotient rule here, but I don't find it particularly useful or fast. I rewrote this as 3 times 2x squared minus 7x plus 5 to the negative 1. And said f prime of x would be negative 3 2x squared minus 7x plus 5 to the negative 2 times the derivative of the inside, which is 4x minus 7. So this is going to give me negative 3 times 4x minus 7 over 2x squared minus 7x plus 5 squared. The derivative at 3 then is negative 3, 12 minus 7 over, let's see, that's 18 minus 12 plus 5 squared. It's going to be negative 3 times 5 over 4. So this is negative 15 over 4. I mean, you can do that using the calculator. Actually, you can just put in f of x is like y1, and then just take the derivative at 3 using the end deriv function on the calculator. You should get the same answer. Let's look at part B. Alright, so part B says find the x-coordinate of each critical value from 1 to 2.5. Alright, so why 1 and 2.5? That's a great thing. Just to be aware, if you took that denominator, 2x squared minus 7x plus 5, and you factor it, it comes out as 2x minus 5 and x minus 1. You can see that in the next part of the problem, like C, they kind of drive that home. But so the reality here is that this thing is continuous between 5 halves and 1, or 1 and 5 halves. So that's why the 1 and the 2.5 are excluded in this. So realistically, the only critical point that you're dealing with here is when the derivative is 0, and the numerator of the derivative was negative 3, that's 4x minus 7. So I want to set that equal to 0. So this is going to be 0 when 4x minus 7 is 0, which is at 7/4. It's the only critical point on what do you call it, on 1 and 2.5. So once you have that, you do have to do something. You got to show that it's either concave down or that f prime goes from positive to negative here. What I just did is I just took the second derivative. I used the nderiv function, took the second derivative of f at 7/4. That yields approximately negative 9.481, which is definitely negative, which tells me I have a local max at that point. So that's how I would handle it. I think that's the easiest route to go on. All right, so let's look at part C. Okay, so part C basically tells you that this is a partial fractions game here. Keep in mind that any points of discontinuity are at 1 and 2.5. So when they're asking you for the integral from 5 up, we are continuous on that interval. And they want that for f of x dx. Okay, so this is where, like, because they already did the partial fraction work for you, you can kind of just throw that in here. All right, so this is a limit, right? So the limit as b approaches infinity, integral of 5 to b of 2 over 2x minus 5 minus 1 over x minus 1 dx. All right, so we do have to do the antiderivative work here. So this is going to become, all right, so the derivative of the inside here is 2, so I get a half out of that, times 2 times the natural log of the absolute value of 2x minus 5 minus the natural log of the absolute value of x minus 1 from 5 to b. Okay, so this cancels. I didn't do this in the work, but I probably should have. This just becomes the natural log of the absolute value of 2x minus 5 over x minus 1 from 5 to b, right? So now I have the limit as b approaches infinity of the natural log of 2b minus 5 over b minus 1 minus the natural log of, let's see, it's 5 over 4. And if you take that limit, this goes to 2, right? So up here, you get the natural log of 2 minus the natural log of 5/4. Now for the AP, that's it. That's all you need. That's as far as you need to go. You can say that this is the natural log of 2 times 4/5, right? Which is the natural log of 8/5. That's probably as simple as you can go in the problem, but that infinite integral does have a solution, which is the natural log of 8/5. So let's look at part D. All right, so part D asks me about n equals 5 to infinity of 3 over 2n squared minus 7n plus 5. And does this converge? Okay, so here's the thing. Let f of x be 3 over 2x squared minus 7x plus 5, right? F of x on the interval 5 to infinity, because note this counter starts at 5, is the following. It's continuous because the only points of discontinuity is 1 and 2.5. So when we're above 5, we're continuous. It is decreasing because this is consistently getting bigger because the x squared dominates in this, right? It is always positive. There's no way to make the numerator negative when I'm above 5 here, right? So it's continuous, decreasing, positive, and the integral from 5 to infinity of f of x dx is non-infinite. It's the natural log of 8 fifths. So we just found that in the last problem. So by the integral test, the series converges. So there's no new work in this. You just have to explicitly state what the integral test says. And once you have that, you can say that this thing converges by the integral test. All right, so in my reality right now, which is probably nowhere near yours, your reality, I think, says that this should be Earth Day, that you're looking at these problems on 4/22. I'm recording this on 4/18 on a dreary Saturday morning at Garrison Forest School. And we just got word from the governor of Maryland and the MSDE state superintendent that we are now backed up to May 15th. So this means that I will not see you personally before the AP exam, which happens on May 12th. So I just, I don't know, it just hits a little small milestone here for me, and I am missing you guys. But I want you to keep digging in because, we're going to get to that exam. We're going to rock it, and we're going to move forward here. So, all right, I hope this helps. Again, send me emails, drop in the drop-in, and we'll keep going from there. Thank you.